So this presentation is called Computation and Graphics Applications. My name is Alex von Hoene. I've studied computer science for 4 years at Indiana University, and currently I'm a Java programmer at the university. I write image processing applications for the biology department. In my spare time, I like to write software in some small and unusual languages, Scheme, C, Forth, Python, a couple of weirder ones once in a while. I also spend a lot of time at the local hackerspace, Blooming Labs, where I recently finished teaching a 9-week course in Blender, which inspired this talk. This is Blender's user interface. Blender is a 3D modeling and rendering application, open source and free software. It's intended to be everything that you need to make movies. It's best known for its 3D modeling capabilities, where you make mesh objects or sculpt in digital clay or create bulk digital particle systems for forests or hair systems or clouds of things. But it also has everything else you might possibly need when making a movie. It has a full render system, including multiple render engines that support things like photorealistic rendering and, physical-based rendering. That's what it's called, PBR. Path tracing, ray tracing. It supports built-in video editing. It has a full-featured physics engine for fluid, wind, and solid body simulation. And significant to today's talk, it has a node compositing system for editing and combining images after they've been rendered but before they've been saved to disk, for things like changing colors, doing green screen effects. So today I'll be talking about the surprising capabilities of Blender for doing computation. So first of all, Blender is much like Vim in the fact that it's modal. Many people find this mindset a helpful way to get in the Blender way of thinking. You have specific parts of your window that do specific things, but at any time you can switch what one portion of your window does, or you can switch your entire layout, which is what I've been doing for my presentation for you, and arrange your Blender for the task at hand. However, in one important sense, Blender is like Emacs. Emacs is deeply scriptable in Emacs Lisp. You can edit Emacs Lisp in Emacs, run it in place, and modify your environment. And Blender is just the same in Python. Underneath, Blender is written in mostly C++ and some legacy C. However, almost the entire user interface is implemented in Python, or at least has Python hooks. So these are a few simple things that I can show. So we can get the objects in the scene. Here's a list of all the stuff. Whoops, new mouse today. We can get an object in the scene. Oh, whoops, it's still on the other scene. Oh well, I'm not going to try and fix that now. This is the more sophisticated version of scripting in Blender, where you actually install a file and run it, and it adds some user interface elements. So this here is a list of 3D scene objects that I can add. And when I run this script, I now get a new object that I can add. Clicking this button adds a tetrahedron. This is new functionality that didn't exist in Blender. This tetrahedron, the mesh that it is, and the button to generate this mesh are both generated by this Python script. And literally everything can be done in Blender in Python, including such crazy things as generating whole three-dimensional scenes using a node compositor-like interface, like what I showed here, that actually compiles nodes into a Python script and runs them to generate objects, apply materials, textures, animations. So this is a very powerful tool for doing computation in Blender. Python is a popular language. You can do whatever you want in it, but it's not particularly interesting. It's exactly like Emacs in that respect, and Emacs is quite old. There are some more interesting things that we can do in Blender as far as computation goes. So for my first demonstration, we're going to be making the Mandelbrot Set. For those who aren't familiar, this is a fractal which lies on a plane where the left is the real number and the up and down are the imaginary numbers. And this fractal is a set of points on this plane, which are computed by this equation. You take a point in the space, and you iterate over and over again by squaring that point and adding it to its original location. Square and add, square and add, square and add, over and over again. And if this point remains bounded as far as where it runs off to, it is a part of the Mandelbrot set. However, if it runs off towards infinity at some point, it is not a member of that set. We're going to be implementing this in Blender's node compositing system as a demonstration of its computational capabilities. And to do that, we're going to simplify this equation in a sense. We're going to make it more complicated in another to avoid having to do imaginary calculations. We're going to do Cartesian calculations. So we're going to do x, which works out as x squared minus y squared plus the original y comes out a little differently. This is just how imaginary multiplication works. And then this is just calculating the distance from the origin to see if it's gone so far away that it can never come back. So we're going to do this. So we're going to open up our nodes, start using them. So the first thing we're going to do is we need a coordinate system. We need to have points so that we can have values to multiply them by. So we're going to create a procedurally generated texture. Starting with, conveniently enough, coordinates. And break this into its components. Whoops, that's the wrong one. Separate. We're going to use red as x and green as y and ignore blue, although if we needed to, blue is z-axis. To get the coordinate system to be scaled differently than 0 to 1 on both, we're going to multiply and subtract. Come on now. There we go. Subtract 2 1/4. And then for the y-axis, it is 2.5 and 1 1/4. So this gives us x and y values represented as red and green colors, which we can then combine back into an image. Which looks like this. This looks rather odd. Why do we have black? Why do we have these weird mixed color high points? This is because generally, as far as image processing goes in Blender, values are represented as values between 0 and 1.0 floating point. For output, they're converted to either 8 or 16-bit integers. But internally, you can use color values that are greater than 1 or less than 0. So this black region here specifically represents color values, point values that are less than 0, which also explains why up here we have no red being mixed in, because the red values past this line are also less than 0. Added to green, all that's left that's positive is the green. But that's okay, as long as we stay internal to Blender and don't export to images and truncate the values, we will have positive and negative values for a coordinate system. And we're going to name this coordinate system xy sub 0 for our initial coordinates, location of every point in the plane. All right, so now we're going to use this texture in our compositing system. First, we're going to set the resolution so the aspect ratio is right, and so that fits on the screen all at once. All right. No. All right. So first we import our texture, the one we made earlier. All right. So this looks good. So now we need to do our equations I talked about earlier, and I just closed that. We're going to take our x values and square them and subtract y squared and add the original x for our x. So first we take our colors and separate them out into our x and y, our red and green. And now we do some math on them. Power of 2. Red, and then green, and then we subtract y squared from x squared. And then we add our original x value. All right, so x squared, y squared, subtract, add x. This will give us our future x value. So we're going to, in the end, combine these. Now we need to do our y. So that was 2 times x times y plus the original y value. So we're going to have some multiplication. And then add the original y value. And then combine this in for our new y-axis. All right, so this has clearly done something bendy. If we duplicate this, then we will start to get a complex color striping shape, which starts to resemble the Mandelbrot set. But again, the Mandelbrot set isn't about just the value of the coordinates when you multiply them and shift them around. It's about where they go. Some of them will go too far away, and they are not part of the set. So we're going to block off the values that are too far away. And the equation for that was just calculate a hypotenuse of a triangle. So for our new x, which was this thing here, and our new y value, we block them off if them squared is greater than the hypotenuse squared. And it just so happens that hypotenuse squared is 2. If you go beyond 2, you've gone too far. Power of 2 x squared, y squared, plus whether or not they are less than 4. All right, so this will create, this value creates values of either 0.0 or 1.0. And we're going to bring that in as an alpha value, as a transparency, so that parts of the shape that are outside of the Mandelbrot set become transparent. And that's it. This is one single iteration of the Mandelbrot set, and we've excluded what's actually an oval, or an oval-shaped part of the plane in a single round of calculations. And if we do this a lot more times, then we'll start to exclude more and more parts of the plane until we've narrowed it down to close to the points that never run off to infinity. So we're going to build some groups here. So this group will be the group that creates the next x value. And then these nodes down here create the next y value. And inputs were the x sub n y sub n and x sub 0, and output is x sub n plus 1, and then same here. So we have x sub n, y sub n, y sub 0. This podium's terrible for the mouse. And y sub n plus 1. And then these guys take in x sub n plus 1, and y sub n plus 1, and output whether or not they've run away. All right. Now I can shrink this down a little, and then we've combined those back into our one image and displayed it. All right, so this is, again, one single iteration. We take in a coordinate system, split it into x and y, iterate x and y, mask them off if they run off to infinity, and combine them back into a picture that we can see. And if we do this more times, then we start to render the Mandelbrot set. So we're going to combine all of these. This has Mandelbrot sub n, and puts out Mandelbrot sub n plus 1. Iterate. All right. So now we have this, and the only problem with this is in here, because for calculating the next x and the next y values, we take in the current x and y values, but also the original x of y and x sub 0 and y sub 0. But because we were designing all this on our first iteration, those are one and the same. That will not be the case in future iterations. So we need to pull these off and have a separate input that will always and forever be the original texture system, original coordinate system. And then the red are the original x values, and the green are the original y values. All right. So now we will always be referencing the actual original coordinate system when we need them, but we'll be taking as an input the previous coordinate system and outputting it to the next for our iteration. So from here on, this becomes really easy. To do more iterations, we can duplicate this and stick it in the middle here. This is looking a little closer, and we can repeat this. And then again. And this is starting to get really slow. These calculations can be GPU accelerated, but my laptop doesn't have that. But we can, since we have many duplicates of nodes inside of our nodes here, since everything in here is identical and everything's in here and so on. We can buffer these nested groups of nodes that we have. And yeah, now it's much faster. So we have 4 and 5, 6. Render in smaller pieces. 7, 8. Hey, this is starting to look pretty good. 9, 10, 11, 12, 13, 14, 15, 16. Oh, it's just about right. The colors are wrong. This is showing where the coordinates have run off to in each place, which isn't exactly what we're interested in. And furthermore, these negative color values are rendering as black or these weird oranges. So for this last point, we're just going to take the alpha values, whether or not they belong or don't belong in the set. We're going to separate out red, green, blue, and alpha in here. And finally, we're going to render this at 100% of its original size. So in this case, it should be 1600 by 900. Oh, never needed those. Oh, I triggered a recompute when I deleted those. There we go. All right, so this is the Mandelbrot set, first calculated in the early 1970s, I believe, on IBM machines. And here we've built the whole thing from scratch using what is essentially an array-oriented programming language for 2 or 3-dimensional arrays of pixel values. And we've done it in 23 minutes using a very curious visual, purely functional, non-Turing complete programming language, which clearly is able to do some useful things like render this image for us based off of some kind of hairy math and quite a lot of it. And also, the node system, being non-Turing complete, doesn't have things like its own built-in iteration, so it can't do looping or recursion. This is why we had to duplicate our calculations 16 times manually. There are additional scripting systems which add loops and recursions to the node system, but not having this guarantees that your render will finish, and it will finish in nearly exactly the same time every time, because it's flowing through exactly the same calculations and matrix multiplications every time. And furthermore, you could estimate how much memory this whole thing will use, because each node needs either 0 or 1 or 2 copies of the image in memory. So you just take the size of your image and multiply by the size of your nodes, and you have a really good idea of precisely how much memory this node system will consume at a maximum, and can guarantee that as long as the implementation of Blender is in line with your understanding of how it's processed, that you can run this calculation on a machine with a minimum of exactly some amount of memory, and it will in fact work every single time. So that was the Mandelbrot set. Non-Turing complete, but visually interesting nonetheless. I feared it'd be a little bit boring if I had just these two things to talk about. You can use Blender as though it was Emacs, but for pictures instead of text. And here's a non-Turing complete programming language that can still do some kind of interesting things. So for the remainder of my talk, I have one more bit of pizzazz, which I'm just going to show. I'm not going to build it from scratch because I spent last night and breakfast and lunch building this today. But this is Blender showing some of its game engine user interface tools. So Blender has a full-featured game engine integrated with physics simulation and the real-time rendering and shading, controls from the keyboard, mouse, joystick, optional output to virtual reality headsets. And it has a kind of similar logic control system, which is all of these down here. This looks a little bit familiar. We have some nodes, and they're connected to each other. There's a flow from the left to the right. It's actually a bit more restricted insofar as nodes can flow only in this direction. Our columns are fixed, and we only have 3 columns. We have what are called sensors and controllers and actuators. You might call them input, Boolean logic, and output. And you're only allowed 1 Boolean logic cell from each input to each output. You can't pipe Booleans back onto other Booleans. But this is a rather more complex and capable system, because you can do things like give objects in a 3-dimensional scene, like this guy here, an internal state, which is what this row here is indicating, a single variable with an integer state. And this has looping and iteration, because when you start the game, it keeps on going until you either explicitly quit it or it crashes, which hopefully never happens. But until then, the physics simulation keeps on running, so this actually has the possibility of being Turing complete. And so, for fun, I've proven that Blender's game engine facilities are Turing complete by implementing a Turing machine. This red cube is the machine. This area of the screen represents a finite portion of the infinite left to right tape. And symbols on the tape are these smaller cubes, which have 2 possible states, low or high. And this cube can move left and right and read whether or not a particular cube on the tape is near or far, and it can push them to be near or far and change their state while moving back and forth. Without further ado, this is a non-terminating Turing machine. It will continue on forever and ever, even on a tape where, in this case, I haven't actually placed definite values outside of these 16 that I've placed. And what it will do is it will create an ever-widening group of values that are the same. And every time it switches direction, it will also toggle all of these values. This is done entirely by logic in the lower left of the screen. The cube has a state, which is shown in the upper left of the game engine render. You can see TM state equals 1. That number will always be either 1 or 0. It has a 1-bit state. And the flow of logic down at the bottom of the screen is for seeing whether a cube is near or far when viewed from the bottom. And if it is moving to the right and the cube is near and it is the right time to make a move, then it will push the cube farther away and scoot to the right. And if it is moving to the left and time to move to the left and the cube is in the far position, then it will jump out and pull the cube to the near position. When it encounters a cube that is not in a position fit to move, then it will switch its state and direction. And this is done as a 3-dimensional scene using the real-time Blender physics engine, the visual logic language. And this is a toy example, but it is in fact a true Turing machine. So this is a much more powerful and also surprising and unusual source of computation in Blender 3D graphics editing animation suite. If worse comes to worse, you can always take your functional programming algorithms, compile them down to a Turing machine transition table and initial state tape, and run it in a physics simulation. That's all I have for today. Thank you.